Alright, hello everyone. So today we're going to talk about, finally, we're going to talk about equivalent resistance. And this is basically a concept made to make, resistor combinations easier to deal with. Alright, so the idea is, I'll explain it. The idea is, so if you have some resistor combination, now uh, it might be anything. It might be a very large resistor combination. It might be a really simple one. But anyways, so you have some combination of resistors. Okay, so some combination of resistors. Use a combination of resistors. Um, it's hard to write that small. I should have actually used the text tool. But anyway, so you have some combination of resistors, and to make this easier to deal with, we're going to try to find a resistor such that a single resistor such that this has exactly the same behavior as the whole combination. Okay, this resistor and the resistance we often often use the symbol R sub eq, the equivalent resistance. So this resistor, this equivalent resistor, needs to have this one resistor needs to have the same behavior as this whole combination. Now, what do I mean by same behavior? This is physics. We cannot leave anything vague. Say for resistors, this means that if we connect if we connect voltage source here, okay, so say a battery. Now this is going to provide some current to the combination of resistors. It will depend on what this combination is. Okay, how much it obstructs or impedes the flow of current. Okay, now the main thing here is this equivalent resistance. If we connect the same battery cross it, okay, with the voltage V, the same voltage, this has to take in the same current. Okay, this equivalent resistor has to be such that it takes in exactly the same current as the whole combination. All right, so that is what makes the behavior the same. Okay, for the resistors. All right, so now we have got an idea of what equivalent resistance is. Okay, but now let's try to see what what the equivalent resistance for the combinations, the two combinations that we have seen so far, series combinations and parallel combinations. What equivalent resistance do they have? All right, so let's see if we can find some formula for them. Right, so first off, for a series combination, okay, I'm going to do the same thing as I did here. Okay, so my combination of resistors is going to be a series combination, right? This is going to be some uh, some combination of resistors which will be in series. So uh, let's just do three for now. Now you could have any number of resistors in series. Let's just do three for now. So you have R1, R2, and R3. Okay. Now we'll connect to find. Now this is going to have this we plan to find the equivalent resistance, right? We plan to find the equivalent resistance. So let's say the equivalent resistance is single resistor R sub eq, right? Now what did I say was the requirement for being the equivalent resistor? This has to have the same voltage current behavior, or I guess it's called current voltage behavior. Anyway, so it needs to have the same IV behavior as our whole combination. So if we connect some battery, the voltage of V, okay, across this combination, let's say that there's a current I here. Okay, let's say there's current I here. Now, as I said just a while ago, this equivalent resistor, if we plug the same battery across it, if we connect the same battery across it, same voltage V, needs to take in the same current. Okay, it needs to take in exactly the same current as here. Okay, so that's all fine and well. And now let's do something interesting. So this is a series connection of resistors. Now we know that the voltage here, the total voltage here, is going to be shared among these three resistors, right? uh, we did see that here the voltage is shared, and as a formula, it's your total voltage is going to be the sum of the voltages across the individual resistors. Alright, so if we say that this is V1, this has a voltage of V1 across it, this has a voltage of V2 across it, and this has a voltage of V3 across it. Okay, you can include the polarities like this, plus minus plus minus plus minus. All right, so if we have uh, if we have this, so we are gonna have V equals V1 plus V2 plus V3. All right. Also, for this equivalent resistor, what is the voltage across it? This cell is only providing the voltage to this resistor, so obviously this is going to have a voltage of V across it, right? Okay, takes in the whole voltage of the cell. All right. So if this is true, let's do something interesting. Let's divide both sides of this equation by the current I. Okay, the current I. So we have V by I equals, I'll use a different color for this side. V by I equals V1 by I plus V2 by I plus V3 by I. Alright, that's all fine and well. Now, what is V1 by I? Okay, this is, if we just look at our diagram right here, what is the current through this resistor R1? Well, this is a series combination, right? This is a series combination of resistors. As we said, if the current through the whole combination is I, the current through each of them, the current is the same throughout a series combination, right? So current through R1, this needs to be I also. So this needs to be I, current through R1. The current through R2 needs to be I. The current through R3 needs to be I. Okay, so all of these have a current of I through them. Alright, so what is V1 by I? The voltage across resistor R1 divided by the current through it, right? That's obviously by Ohm's law, that is going to be the resistance, right? The resistance, which is R1, and same thing happens here. This is going to be R2, voltage across R2 divided by the resistance through it. So that, sorry, no, the current through it. That's going to be the resistance. So that's R2. So this is R3. And what is V by I? Well, just look here. V was the voltage across the equivalent resistance, right? The equivalent resistor. And this has a current of I through it. So by Ohm's law, V by I has to be the value, right? This value R sub EQ. This resistance value R sub EQ. So we have this fairly neat formula. Okay, we have this fairly neat formula we just proved for the equivalent resistance in the series combination. So this is going to be equal to the sum of the individual resistances. That's pretty neat. Okay, so in a series combination of resistors, your equivalent resistance is going to be the sum of the individual resistance. And as I said before, you could have as many resistors in series as you like. You could have, if like if there were n resistors, you'd add them all up. Okay, add them all up. So anyways, that aside, we just got our formula. Let's try using it. Let's try using it in a problem. So we have, let's see, this circuit. We have resistance here, and a resistance here, and we have voltage source right here. Okay, so this is 1 ohm, this is 1 ohm, this is 4 ohm, and this is 5 ohms. All right, so, and this is 5 volts, this is 5 volts. What we need to do is figure out the current through the resistor combination or the current provided by the battery. It's all the same. Well, we could actually, even without this equivalent resistance formula, we could have actually solved this problem, okay? Because we know that the current through them is the same. So if you use Ohm's law, you could find the voltage through this. That would be 1I, this would be 4I, this would be 5I. Adding all of them up, since the voltage is shared, you could equate them to 5 volts, the total voltage, then you'd get I. But instead of that cumbersome process, and as you'll see later, for if you have mixed resistors, as we'll see, when the combination becomes more complex, doing this using these elementary methods isn't really feasible. Okay, it's not like it wouldn't work, it just would take a lot of time and energy. So uh, that's what equivalent resistance is for, just to simplify these problems. So this a combination of series resistors, we can say that this is going to be, we can replace this by a single equivalent resistor, right? Single equivalent resistor, and with the same, we will have the same voltage source here. Okay, and this will give the same behavior, same current. Okay, now what I want to do first is obviously find the value of that equivalent resistor, right? So that is going to be our R sub EQ is going to be just the sum of all the resistors in series, right? So 1 plus 4 plus 5. So 1 plus 4 plus 5. So that is 10 ohms. That is 10 ohms. So that is going to be the value, the resistance of this equivalent resistor, that's 10 ohms. Now, from this circuit, you can obviously easily find I. So Ohm's law gives us that, Ohm's law tells us, so the voltage across this is obviously 5 volts, and Ohm's law tells us that the current must be 5 by 10, right? V by I. So 5 by 10, and that is 0.5 amps. 0, oops, 0.5 amps. All right. So that problem is solved, and these are really fairly simple. From equivalent resistance, dealing with resistors in series is the easiest thing to do. It really, unsurprisingly, since the formula is so simple, it's just a simple addition of, or simple sum of all the individual resistors. For the series combination is the easiest to deal with among all the combinations. And well, but let's see something interesting. We dealt with this before. Before we saw that if for some reason you have a part of your circuit, there's a gap opens up. Maybe it's due to turning off a switch, or maybe something gets damaged. But let's also see this in another way. Let's try to see this in light of our equivalent resistance formula. Suppose, say, if in some combination of resistors, okay, you have this open circuit, okay, open circuit. This is circuit element, okay. As I said before, not it's not a circuit itself. So it's basically uh, something, it's a gap, okay, and it will have infinite resistance, okay, it will have infinite resistance, okay. So that's basically an open circuit. We discussed that before. You If If you didn't catch that, please do check out the series resistors video. And now, well, what I want to do is find out the equivalent resistance for this combination. And we could label these resistors, but we really don't need to. It's just a very simple logic. Okay, this is itself, you could treat it as a resistor. Okay, this is a resistor with infinite resistance. Okay, that's basically what an open circuit is. Okay, it's basically a theoretical resistor which has infinite resistance. So we have an infinite resistance plus, it really doesn't matter what these are, right? What these other ones are, whether it's 1 or it's 10 to the 6, or it really doesn't matter what the other resistances are. Since you have one infinity, you have an infinite resistance here already. Whatever you add with this to find the equivalent resistance of this series combination, you're going to end up with still end up with infinity. Okay, it wouldn't make a difference. The others wouldn't make a difference. So that's why the resistance, when you have any, for any reason, you have an open circuit in a series combination, your resistance becomes infinity. That also explains why you don't, no, it doesn't, there, no current would flow through. Okay, the whole series combination stops working or stops receiving any current, because uh, due to the open circuit, it has an infinite resistance. All right, so I think that's enough discussion for series circuit.